Okay, so we introduced the 6 basic trigonometric functions in the previous videos. Now we're just going to talk a bit about their inverses. So if you studied functions already and inverse functions, you'll know that a function can only have an inverse on a domain on which it's 1 to 1. So just a quick revision example. We'll take the function y equals x squared, right? I'll try and do a very rudimentary sketch of this function. So when does it have an inverse? Well, it can only have an inverse where it's 1 to 1. So let's pick everywhere where it's greater than 0, and then we can define an inverse function there. It'll just be the square root function, right? Now the reason why I can't define it when y equals x squared goes from many to 1, if we take, for example, the point, I guess that might be 4, we can see that either 2 or minus 2 would have give you 4, right? If I square 2 or I square minus 2, I also get 4. So I can't really have a function that takes 4 to 2 different values. I need to restrict that function to a domain where it's 1 to 1. But we know that from inverse functions, right? From our work in inverse functions. Now if we take the function y equals sine of x, and I'll draw a quick sort of rudimentary, again, sketch of this. We have a couple of choices for our domain to pick where it's going to be 1 to 1. But traditionally we're going to go with this. Okay, so we're going to take that chunk of it there where it's 1 to 1. Now notice if I go outside that chunk, then I've got a value. For example, I don't know, this one. If I was to go outside that, I've now got a value that is actually hit twice, which is not allowed. Okay, so we have to keep it in this range, and notice the range we're dealing with there. That's going to be basically 90 degrees to minus 90 degrees. Okay, and the function, so we'll give it a name, and it's called arcsin. Y equals arcsin of x. So that would be the inverse function of sine. So it kind of does the opposite of what you think sine does. It takes in numbers from minus 1 to 1, and it will pop out an angle between minus 90 and 90. Okay, now notice that arcsine of, let's say, 1/2. So we know from the previous videos that sine of 30 degrees gives a half. So arcsine of a half is 30 degrees. But we could also have sine of, well, this says that sine of 30 degrees is a half, for sure. But we also have other values that will actually give a half as well, because sine's a wave. So we just go a bit further along the graph, we can get another value that is also a half. And that's okay, because we've restricted the domain to make this inverse function. So remember that this isn't going to give you all the possible values that your angle could have been, because there's infinitely many values that your angle could have been. It's only going to give you the one value inside this range, inside these two dotted lines, and that value is sometimes known as the principal value. Okay, but this is the inverse function. Now we could probably draw a sketch of it, and a trick to sketch inverse function is literally just to pick the line y equals x and make your function kind of reflected in that, right? So we know it's going to look a bit like this, but let's set up the axis properly. So would I suggest remembering this function, or would I suggest re-deriving it from first principles? It's tricky to say. I'm not really sure. It's up to you in that one. Just look at what sine did. We're going to do the opposite, okay? It's going to be here and here. Small segment. We're just going to be like this, right? And notice that on this axis, it's going to be a 1. It's going to be a minus 1, not in this axis. This will be 90 degrees, and this will be minus 90 degrees. And that is inverse sine, the inverse function of sine, or arcsin. So now I've introduced that. Okay. So that is just, by definition, the inverse function of sine. And similarly, we can do one for cosine. So let's pick, again, a region of the cos graph where it is 1 to 1. Okay. I notice we can't go either side of the origin because already we're facing problems. And because the length of the segment we picked for the sine graph was 180 degrees, we would also assume that to be true for cosine as well. Okay, so indeed it is. We'll go with this chunk here, so between these two dashed lines here, and on this region the function's 1 to 1, so between 0 and 180 degrees. Okay. Yeah, another question is, so this function will be arccos. Now we'd like to sketch it. Okay, so what's that going to look like? Well, remember, when I put in 0, I'm getting out 1. And when I put in 180, I'm getting out -1 for cos. So to sketch arccos, mark on those two values, and then the rest of it you can kind of fill in, right? So I know the arccos of 1. Yeah, arccos of 1 is going to be 0. So I'm going to put that here. I know that arccos, let me think. This always kind of a bit fiddly. Yeah, arccos of -1 is going to be 180. So it'll look like this. Yeah. Okay. So -1, 1. We have up here being 180 degrees. And of course it goes through the origin 90 degrees. Okay, so that's arccos. Again, it gives you the principal value. So an example would be, arccos of a half. That'll give you 60 degrees. Why? Because a half's about here, and that would be that value. And also we know that cos of 60 is a half, and we can remember that because sine of 30 is a half, and it's a complement from 90 degrees. Yeah, and of course other values of cos can also give you half, but remember this is just going to return the principal value. So pretty damn important. Get your head around that. And then let's do arctan just for completeness. So again, tan's a little different than sine and cos. So we're gonna have, remember, tan had these asymptotes at intervals of 90 degrees, well, every 180 degrees, sorry. And it's not too bad really. This is an easy inverse graph to do. In fact, if this was tan, you can literally just see that the inverse tan function is going to be really similar. It's just going to be drawing these lines in. The asymptotes have to be in the same place, right? And we're just going to have this kind of thing happening. Nope, that's totally wrong. I'm thinking of 1 over tan. Apologies. No, what we're gonna get here is, if this is 90 degrees, yeah, my mindset's thinking of the cotan function. Okay, if this is 90 degrees here and here, remember that tan can actually get out any value. Okay, so here in this region of the graph, it's tending upwards to infinity. Here it's tending down to minus infinity. Now, what's going to happen is that it never quite reaches 90 degrees. So there isn't a value of tan of 90, and as such, there's never a value that you can get when you take arctan that'll pop out 90. So that's actually an asymptote on the inverse function graph. And it's quite easy to draw. I say that even though I drew it incorrectly the first time, but no, this should make sense. Right? You'll have these asymptotes at 90 and minus 90 that time will never quite get to. Yeah, I think I'll leave that mistake in the video for authenticity. Right? And it's just gonna go like this, never quite touching those asymptotes. Hope my graph sketching is okay. For the software I'm using, it's quite difficult to do things neatly, but I don't think that matters too much as long as I'm getting the main ideas across here. So this is inverse tan or arctan. Okay, now notice we've again needed to restrict the domain, so it's 1-to-1 in this region. But this time it looks different because arctan can take any value, right? So the domain can be any real number here, and it's going to pop out something between minus 90 and 90, right? Going up here, the domain of arccos is of course between minus 1 and 1, and arcsin's between minus 1 and 1. The reason for that is that the sine and cosine functions are bounded between minus 1 and 1. So if I try to calculate something like arccos of 2, I know I can't actually do that. Okay, so to write this, at least in terms of the tools we're developing here, this doesn't really make any sense because there wasn't a value I put in that could have given me arccos, that could have given me 2 out into the cosine function, right? But for arctan, this isn't a problem. Now this is the graph of cotan, right, or cot. And similarly, you can have arccot, you can have arcsec, you can have arccosec, right? But those functions generally don't come up too much. Really, what you wanna get in your mind is the graphs for arccos, arcsine, arctan, and you want to start being able to use them in simple, basic trigonometric problems, as we're gonna cover. But again, we're just building up the toolkit for you to start tackling some trigonometry problems here. So I hope this was helpful.